Okay, in section 5 we're going to complete our look at polynomials by trying to find all the zeros of polynomial functions. So this will include rational zeros, irrational zeros, and complex zeros as well. So this really all comes down to one of the most important theories in math, which is called the fundamental theorem of algebra. Now the fundamental theorem of algebra, it's a pretty simple theorem. It says all polynomial functions we'll call them f of x, have at least one zero in the complex number set. So if we take any polynomial that exists, so any combination of variables and numbers and positive powers, any of those, I will always get a zero, at least one zero for this polynomial. So this is actually a very difficult theorem to prove. It does a lot of what's called abstract algebra, so we will not prove it in this class. But just know it says that all of them have at least one zero in the complex number set. Well, this might seem like kind of an odd thing, because let's say we had this polynomial f of x equal x to the third minus 2x plus 1. We knew by the degree that this thing has, at most 3 real zeros, but it never said that it was guaranteed to have any. So this is the first theorem that kind of guarantees that there is one. Actually, by a consequence of the fundamental theorem of algebra, if you think about every polynomial having a zero, well, if I factor that zero out, then I can actually find all the zeros that would actually be the same number as this degree. So one of the important consequences of the fundamental theorem of algebra is any polynomial function we'll call it f of x again, has exactly n roots in the complex number set. So complex number just means it could be real, it could be complex with an I, any of those are possible. So exactly n roots in the complex number set where n is the degree. So this polynomial example I gave you above, x to the third minus 2x plus 1, there is exactly 3 roots of this in the complex number set. Now it could be 1, it could be 2, it could be 3 plus 2i. All these are possibilities, I'm not really sure. We will have to figure out, and really in this section we'll do some examples where we find all these zeros. We will be very dependent on our Desmos calculator, any graphing calculator, to try to help us out. Otherwise, we'd have quite a lot of things to plug in and calculate. Okay, let's look at an example of one. So we have a function, and we have the function x cubed plus 6x plus 20. So if you look at this, the degree of this function, the degree is obviously 3. It's the highest power in the polynomial. So by a consequence of the fundamental theorem of algebra, like we talked about earlier, that this f of x has precisely 3 zeros in the complex number set, because the degree is 3, so there's 3 zeros. So our goal is to find 3 zeros. And of those 3 zeros, at most 3 of them are real. Okay? So we are really looking for 3 real zeros. But there could be less. And I'm pretty sure in this case there will be less. Okay? So what we'll do here is we will look for some different rational roots. So the first thing I'll do is I'll look for factors of p and q. P is the factors of the constant. So I have this written backwards. So this is our p. P is 20, and q is the leading coefficient, which is 1. So the factors of p, so what multiplies to give you 20 could be 1 and 20. So I put plus or minus 1 and 20. I put plus or minus 2 and 10. What else multiplies to 20? It would be 5 and 4. Now what multiplies to 1 is very simple. It's just plus or minus 1. So what we do is we take all the factors that are of the last number and all the factors of the first number and we divide them. So if I take 120 and all those and divide it by just 1, then my list of possible rational zeros is just going to be plus or minus 1, plus or minus 20, plus or minus 2, plus or minus 10, plus or minus 5, plus or minus 4. So if there are any real zeros, then they would have to be in this list. Okay? Now the question is, how do I know if any of these are real zeros? How do I know if any of them work? That is the goal. Okay? So we can look at the first one. We can say, is x equals 0 a factor? This is always a nice one to get rid of, and it's a no. If I plug in 0, I don't get 0, as you can see, because 0 plus 20 is not 0. Okay? So it's not. But that's always something we should look at because it makes our life a little easier. So what I want to know is, of this list of roots, are any of them zeros? Okay, are any of them zeros? So what I went ahead and go do, I am going to plug in all these numbers if you want. I'm not going to do that. What I'm going to do is I'm going to graph this function. So when I graph it, I'm just going to kind of sketch it here. So the graph looks something like this. So it only crosses one spot. So one of the zeros they have, because I know f of 0, or f of negative 2 equals 0. Now how do I know that? I know that because when I looked at my graph, it crossed at negative 2. So one of my zeros, I'm looking for 3 zeros, remember, one of them has to be negative 2. So I have to find 2 other zeros. Now the graph does not cross any other places on the graph. It only crosses that one place. So what we have to do now is we have to use synthetic division to find out what the other 2 are. And this is where we're going to use our quadratic formula, our synthetic division, all the tools we've learned in this chapter so far. So right now, we know one of the zeros, right? So we'll list all the zeros. One of them we know is negative 2 because it crossed the axis at negative 2. We have to look for the other ones. Alright, so what I'm going to do is I am going to divide out the one root I know. The one root I know is negative 2. So if I divide that out into my polynomial, which if you recall was x cubed plus 6x plus 20. So my numbers I'll put up there are 1 for the x cubed, 0 for the x squared, 6 for the x, and 20 for the constant. Just make sure we got that right. 1, 0, 6, 20. So we're going to go ahead and synthetically divide that. We'll bring down the 1. Negative 2 times 1 is negative 2. 0 plus negative 2 is negative 2. Negative 2 times negative 2 is positive 4. 6 plus 4 is 10. Negative 2 times 10 is negative 20. So we're left with a remainder of 0, which makes sense because if you remember, our polynomial has a factor at negative, or a 0 at negative 2, so when you divide it out, you should get a remainder of 0. So right now, our remaining polynomial here, we started with a cube, we divided once, so this is going to be x squared minus 2x plus 10. It's a quadratic. So our two factors we have so far is we have x plus 2, because remember we had this negative 2 as a root, so we're going to put that as a factor. And we of course have x squared minus 2x plus 10. Now we've only found one of our 3 zeros. We have to find the other 2 zeros from this quadratic. But it's quite simple because now we'll just use our quadratic formula. So what we're going to try to do is we're going to try to figure out when is x squared minus 2x plus 10 equal to 0. So if you use quadratic formula, this is going to be negative b, so negative negative 2 is a positive 2, plus or minus the square root of negative 2 squared, minus 4 times a times c, all over 2a, which is 2 times 1. So if I work this out, this is 2 plus or minus. The stuff inside the root becomes 4 minus 40, which is negative 36 over 2. So this is 2 plus or minus. The square root of negative 36 is 6i divided by 2. We divide them both by 2, we get 1 plus or minus 3i. So my other two zeros, I found them now. They're complex, and that makes sense, because if they weren't complex, they would cross the axis. We have 1 plus 3i, 1 minus 3i. So we just found 3 zeros. So no matter what your degree is, you can find them all. And if I want, I can actually write my polynomial in factored form. This would be kind of a bizarre factorization, but if you remember, our original polynomial was x cubed plus 6x plus 20. So I know that factors now is those three factors, x plus 2, of course. And now I found these complex roots, so I can factor this as x minus 1 plus 3i and x minus 1 minus 3i. So if you want to write it in factored form, once you know all these zeros, you just basically take x minus each of the zeros, and we are done. So really nothing new in this section. We're just kind of going through a lot of the different things we've learned this chapter and putting them all together. Okay, let's look at another one. This one actually, even though it looks a little more complicated, it's got a higher degree. So it's a higher degree, it has a degree 4, so we're looking for 4 zeros. This is actually a really easy problem. And all the work is going to be done by my calculator. So by the consequence of the fundamental theorem of algebra, this polynomial has 4 complex zeros, because the degree is 4. And at most, 4 of those are real. So it could be 4, it could be 2, it could be none. Now, is x equals 0 a factor in this case? In this case it is, because you notice they all have an x. And when they all have an x, then if I put a 0 for all the x's, obviously the function is going to be 0. So what I like to do is anytime you have this x, I want to factor it out, because I really don't want to deal with it. So if I factor it out, I get 3x to the third plus 20x squared minus 36x plus 16. So now if you look at this, I already know one of the zeros, right? So if I go down to the bottom here, it says list all the zeros. Well, cool, I already know one. I already know it's 0 because I had a factor. It said, what's the factorization? Well, I know one of the factors has to be x because I just factored it out just using GCF factoring. So now that I know one of them, I'm going to look at the polynomial inside. Now I'm only looking for 3 more zeros. And so we'll go through the same process we went through last time. We'll look at which zeros are possible. We'll plug them in the calculator, see which ones work, and we'll see if we need to find how many more we have to find. So remember, this is our p. Our p is our last number, and our q is our first number. So the factors of p, the factor of 16 is going to be 1 and 16, 2 and 8, and 4, and of course 4. The factors of 3 are just 1 and 3. So now I'm going to divide all the factors of p by all the factors of q. So if I do that, I'm going to take 1 through 4, and I'm going to divide them by 1, and then divide them by 3. So I have a lot of possibilities this time. I have 1, I have 16, and these are both plus and minus, 2, 8, 4, but then I'll divide them all by 3. So 1 over 3, 16 over 3, 2 over 3, 8 over 3, and 4 over 3. So all of these are possible. So what I'm going to do is I know if the graph is going to cross at any rational number on the graph, it's going to cross at one of these. But interestingly enough, when I look at the graph, I actually see 3 zeros where it crosses. This graph, now, what I would do is I highly suggest you put this into Desmos right now. Pause the video, put it into Desmos. Look where the graph crosses. I see that it crosses at these 3 intercepts, 2/3 and 0, 4 and 0, and 2 and 0. It crosses at all 3 of those intercepts. So I know that all 3 of those must be 0. And if you notice, those are all on my list. We got a 4 there, we got a 2/3, It says 0.67, but we know that's 2/3. And we also have a 2. So all of those were possible zeros, so it makes sense that those all could work out. So now I know more zeros. I actually know down here, I actually know that 2/3 is a 0, I know 2 is a 0, and I know 4 is a 0. So I know all 4 zeros. So if you recall, we were just looking for 4 total, so we are actually done. So in this case, we do not need to synthetically divide because we've already found all the zeros. Now, if you have complex or irrational zeros, you will not get this lucky. In this case, this was a nice one. Everything worked out pretty nicely. Okay? So what I'll do now is I want to write the complete factorization, which is not tricky, but the one thing I want to be careful of, so I know x minus 2 is a factor and x minus 4 is a factor. Now, you can do this last one, the 2/3, a lot of ways. The easiest way is to just write the x minus 2/3. But I will claim to you, if I FOIL this out, I will not get the same number as I got way up at the top. Because you notice the first term is -3, and I have just x, 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 x. So what you want to do to make sure this is factored correctly, whatever the number is in front, in this case it was -3, you just want to tack that -3 right out front. So this would be the factorization. Now, quite honestly, we're more interested in these zeros and which ones are real and which ones are complex. But again, in this problem, most of them are just found by graphing it. Okay, let's look at our last one. We have x to the 4th minus 5x squared minus 36. So again, highest degree is 4. So we can have at most 4 real zeros. And has precisely 4 zeros in the complex number system. So we're going to have 4 zeros. We're not sure if they're real, complex, combination of the two. We'll have to find that out. And again, remember, this is all from the fundamental theorem of algebra. There are actually 3 major fundamental theorems of calculus, algebra, and arithmetic. This is one of the big ones. So first thing I'll do is I'll look for all the possible rational zeros of f of x. So these are my p's and this is my q. Now q in this case is just 1. That's nice. So really all I'm looking for is factors of 36. So the possible factors of 36 are 1 and 36, 2 and 18, 3 and 12, and 6 and 6. And again, this is just from the rational roots test. But we really like the rational roots that work out because we can just look at our calculator and see which ones work. So again, right now I would pause the video, put this into Desmos, type your x to the 4th minus 5x squared minus 36. So if you've done that, I see that this graph crosses 2 places. It crosses at 3, 0 and -3, 0. Only 2 places though. It does not give me the other 2. So I only know 2 zeros right now. I know 3 and I know -3. I'm missing 2 more. So we're not going to get as lucky as we did in the last one where we knew them all. We'll have to use our synthetic division. So we'll start with 3, and I'm going to divide 3 into my polynomial. Now remember how we write the polynomial. We write 1, I make a 0 because there's no x cubed, -5, a 0 because there's no x, and a -36. So I bring down the 1, 3 times 1 is 3, 0 plus 3 is 3, 3 times 3 is 9, -5 plus 9 is 4, 3 times 4 is 12, 0 plus 12 is 12, 3 times 12 is 36. And that should make sense because that was a 0, 3 was a 0, so it should give us a remainder of 0. Now interestingly in this case, I know another 0. So whatever numbers I have remaining, so I have this 1, 3, 4, and 12 remaining, I'm going to immediately divide the other one, the -3. So I bring down the 1, -3 times 1 is -3, I get 0. -3 times 0 is 0, 4 plus 0 is 4. -3 times 4 is 12, and I get another 0. So I divide both of them out, and I end up with 104. But what this really means is this is x squared plus 0x plus 4. So what I've just found is I've found a quadratic that will find my other two zeros. So I took both zeros I found simply just from the graphing, or the graph of it on the calculator, and now I end up with this. So to find the other two zeros, just like I did on the first problem, I'll take x squared plus 4 and set it equal to 0. Now again, remember, the degree of this is 2 because we started with a 4 and I divided out twice. That's why it goes down to a 2. It is not a 3. So you could use quadratic formula, but this one's super easy to actually solve because I could just subtract 4 from both sides because there's no x term. Take the square root. X equals plus or minus 2i. So these would not appear as intercepts on the graph, but they are certainly zeros. If I plug in 2i or negative 2i, they give me 0. So now I have all 4 roots. 3, negative 3, 2i, and negative 2i. So now if I want to write this as a factorization, I can just write each of these as x minus its root. So x minus 3, x minus negative 3 is x plus 3, x minus 2i, x plus 2i. So again, we kind of use technology to obviously aid our work, but to find these complex and irrational, you have to do this synthetic division. You have to be able to use the quadratic formula. All right, that is all for section 5. If you have questions, please let us know.